Okay. Hello and welcome to today's ACM SIGSOFT webinar. This webcast is part of ACM SIGSOFT's commitment to provide value to its current and future members. The ACM SIGSOFT webinar series features speakers from the Future of Software Engineering track at the International Conference of Software Engineering, as well as select keynote speakers and distinguished paper authors. I'm Brad Myers, a professor in the Human-Computer Interaction Institute in the School of Computer Science at Carnegie Mellon University. I'm also the principal investigator for the Natural Programming Project and the Pebbles Handheld Computer Project, and I previously led other projects like Amulet and Garnet. It's my pleasure to welcome you today, and especially to be moderating this session with Professor Margaret Burnett, with whom I've been collaborating for many years. Before we get started, I'd like to quickly mention a few housekeeping items that you can also see on the slide in front of you. The slides will advance automatically throughout the event. On the bottom panel, you'll find a number of widgets and resources. At the end of our presentation, we will have time for questions. Please type your questions into the Q&A box at any time and click on the Submit button, and I will organize the questions and ask Margaret the ones that seem most interesting. The session is being recorded and will be archived, and you will receive an automatic email notification when it is available. And you can also check www.sigsoft.org/webinars.html in a few days, and you can see the updates there too. A copy of today's slide deck is available in the resources list widget. It looks like a little green folder at the bottom of your screen. Okay, today's presentation is titled End User Software Engineering Beyond the Silos, and it will be presented by Professor Margaret Burnett. Dr. Burnett is Professor of Computer Science at Oregon State University and one of the co-founders of the area of End User Software Engineering. Her team's What You See is What You Test, or WYSIWYT, is a systematic testing approach for end user programmers, and it initiated the groundwork, and in 2003, she co-founded and became the project director of the EUSE consortium. Under her leadership, this consortium, this collaboration, has grown to over 10 institutions, and their contributions have helped ordinary end users achieve up to 10 times greater effectiveness at guarding against software defects. Professor Burnett also serves on several editorial boards in both software engineering and HCI, including the IEEE's Transactions on Software Engineering and ACM's Transactions on Interactive Intelligent Systems, and also is a member of the National Center for Women in IT Academic Advisory Board. Margaret, we're looking forward to your presentation, and why don't you start?
Okay, great. Thank you, Brad, and welcome everybody. So as Brad mentioned, today I'm going to talk about kind of a future vision, or maybe ideas for future visions for end-user software engineering and getting beyond the silos. This is based on a paper that Brad and I wrote together as part of the Future of Software Engineering track that he mentioned. And in the very, very, very last slide, there'll be a link that you can click on or copy or whatever to that paper if you want to read it later on. So let's start off with a brief whirlwind tour of end-user software engineering as it exists today and even why it exists. So it all started with end-user programming, in which a lot of researchers and other kinds of tool builders decided that it would be great to enable ordinary end users to create new programs. And there the emphasis really was on create programs by themselves. And these efforts were quite successful, and today end users can write a lot of programs. In fact, there are more end-user programmers today even than professional programmers. And just to give a taste of some of the, shall we say, integrated development environments that they use, one example is CoScriptor, which is a great example of programming by demonstration. So this is a teeny little screen. Don't try to read it. All I'm showing you is that there's a web page that's part of it. And as the user does stuff, it gets recorded because they pushed a record button, and it generates program lines, which they can then edit if they want to make them more general. So that's one example, quite representative of programming by demonstration. Another example is LabVIEW, which is a visual data flow language from National Instruments, and it's intended for people like laboratory technicians and scientists. So there are these teensy little things over there on the left which represent what they call virtual instruments. And so you hook a bunch of wires that are hooked to sensors into your computer, and then LabVIEW has those little nodes that the sensor data comes into, and then you wire them up to a variety of functions to get the computations that you want based on those. And then, of course, there's the ubiquitous spreadsheet, and some of you may not think of that right away as end-user programming, but in fact, every time somebody puts a formula into a spreadsheet, that's an example of first-order functional programming. So that gives an idea, but the problem, and this is the thing that spawned end-user software engineering, is that the programs that people write using environments like those tend to be very undependable, lots and lots of errors. So at that stage, without adding any kind of software engineering or quality capabilities to these kinds of environments, what we can say is that end-user programming is empowering ordinary end users to use bad programs to make bad decisions. And in fact, this phenomenon is even compounded by the pervasive human tendency to be overconfident in anything that they do. So just to give a few examples of this lack of dependability, you all may remember Hurricane Katrina, a natural disaster that took place several years ago. And in the wake of that event, a lot of people, ordinary people, sprang forth with cobbled together websites listing survivors' last known locations and status. But a problem was confusion just reigned because a lot of the data was inaccurate or missing, and the various sites couldn't really leverage each other's knowledge because everybody had used different kinds of formats and different data conventions. And so, it was really impossible for people to be able to get themselves out of that hole. Another situation that occurred in the spreadsheet, there's a village in Wisconsin called West Baraboo, and they had a budgeting spreadsheet with a formula error, and this caused them to underestimate the borrowing cost of a decision they had made by $400,000. So that was very bad. That's, of course, based in spreadsheets. And then, of course, faulty business applications, things that just lead to, say, permissions problems or page not found, cause lost revenue and lost credibility and therefore hurt the businesses. So those are just a few examples, and those kinds of examples are what led to this sub-area about 10 years ago called end-user software engineering. And here are some pictures of a whole lot of people that have helped to contribute to that area. So you have a picture of Brad Myers. Can you see my mouse right now circling around Brad? Maybe not. Mary Shaw and Andy Coe, Chris Scafidi. There's a picture of me with one of my students, Danny Digg, Sebastian Elbaum, Feline Hermans, Yvonne Dittrich, Gregor Engels, and Stefan Sauer. So lots of people all over the world started working on that project and really coming together at about that time. And the question that really brought these people together was the following. Is it possible, and if it is, how, can we bring the benefits of rigorous software engineering methodologies to ordinary end users? So some of you may not have run across end-user software engineering before, so I'm going to give just a very quick example of the first one, at least the first one I know about, which is WYSIWYT, the project that Brad mentioned during the introduction. This is something I did with Greg Rothermel. It's called What You See Is What You Test. And the idea there was to bring systematic, rigorous testing capabilities to spreadsheets. And so we started with testing theory, and one of the things we had to do at the very beginning was decide, well, in this world with end users and spreadsheets, what is a test even? And we decided that in that world, a test had to be a decision that the user made, that some output is right given the input. So in kind of classic testing, a lot of times it's just the presence of output, but here we needed to make sure that we knew that the users had put their eyes on it and made a decision. And so the way that we did that in our system, our WYSIWYT system, was we said, okay, they've got to check it off. And if they check it off, we know they've made that decision. Then that leads to the question of, well, what's enough testing? So of course, most of you probably know you really can't prove correctness of programs through testing. So there has to be some kind of notion of, well, when has somebody tested enough? And so we borrowed something from classic software engineering called definition use adequacy, which really has to do with dependencies, both data dependencies and control flow dependencies. So having done the definitions, we put together a system based on them, and I'll just show you a quick demo. So here we are in a spreadsheet, but we have these kind of funny border colors and funky little check boxes. And so the user doesn't have to notice those things, and they can just go about their business, but they might notice them. And if they do, they can hover over, because the whole thing is supported by tooltips. So if they hovered over one of those little check boxes, it says, if this value is right, check it off. If it's wrong, exit out. This testing helps you find errors. So if they do check it off, which they can do at any time, that's their way of saying, yes, this value here, this is right. And if that happens, then the borders change colors to reflect testedness. So what the users need to know, and this too is told to them in tooltips, is that red borders mean untested and blue borders mean tested, and anything in between means in between. So if their test has added more coverage of the dependencies, then that cell border will turn more blue. And the testing kind of swims upstream against the dependencies. So other cells that affected that cell, if the test covered some more dependencies in those chains too, then those will turn closer to blue. So that's really worked out quite well. There have been any number of empirical studies on WYSIWYT and its derivatives. And what it's shown is that this approach has been actually useful, usable, and effective by ordinary end users. So that's great. But that's end user software engineering today. What about a future beyond kind of a siloed approach? So what is a silo? Well, it's a system or process that operates in isolation from others. And what a lot of end-user software engineering work today does is it works inside of these kind of lifecycle cycles. Wow, lifecycle silos. There we go. So a silo about design, a silo about testing, like the one you just saw. And these silos, these can be quite helpful when we're really trying to isolate and focus our efforts, but the risk is that they lead to tunnel vision, a lost potential for big, outside-the-box kind of gains. So in this talk, I'm going to be talking about what kind of challenges there are for de-siloing the future of end-user software engineering and what benefits might come about from a who perspective, a when perspective, and a why and how perspective. So let's start, down with silos. There we go. So let's start with who. So some basics. End-user software engineering has parents both in the software engineering realm and the HCI realm. And from HCI, it inherits the importance of this notion of who. There are two key requirements that are pretty well known already today in end-user software engineering about who. One of them is we can't assume that the users of end-user programming environments have any software engineering skills. They might, but they might not. And the second basic is that end-user software engineering tools and techniques must fit the interests and the motivations and the practices of the end-user developers that are sitting in front of them. So who exactly are these end-user developers? Well, first I'm going to talk about some assumptions that are not true. One assumption that you sometimes see is that people think, well, they're people who wish they could program better. But this is often not the case, so that assumption is not good. In fact, there's a different name for people like that. They're called novice programmers. That's not normally who end-user developers are. A second assumption that also is not really a very good one is that they're people who don't program. Well, this is sometimes true, but not always. There are lots of examples, such as let's say, lab technicians who have had some programming background, but they aren't in a professional programming situation. Now, if we don't know who they are, we can't build tools for them, and that's kind of a basic from HCI. So in today's end-user software engineering, we have an answer to who they are. We do empirical studies, targeted studies, to understand those people's needs and create tools based on them. And so lots of examples of that exist in the end-user software engineering literature. Teachers, designers, children, lab technicians, all different kinds of people. And these techniques reveal very important information, and a great thing is the resulting tools fit those audiences' motivations and practices. So that's gotten us a fair distance. But it does have this disadvantage because it's kind of promoting the silos. Each population is sort of researched separately, and it has a tendency sometimes to silo our knowledge by population. So we're trying to get outside of those silos. So how can we do that? So there are my little silos by population. So there's a great hint in the real definition of end-user developers. I haven't really defined that for you yet, but there are a couple of very well-known researchers, Bonnie Nardi and Andy Coe, who have put forth definitions of end-user developers, and those definitions emphasize intent, not programming experience. And so both of them say that end-user developers are people whose deliverable, whose reason for programming, is the result of the program, not the software itself. So that's how they differ from professional developers. And so as we think about that definition, we realize, and they point out, that end-user development is really a role, not a personal identity. And so we can use this. This gives us a great insight because this nuances this whole notion of who. It shows that even people who program regularly sometimes are in an end-user development situation. So for example, I have a PhD in computer science, but sometimes, say for example, when I'm working with spreadsheets, I'm not really using my computer science habits the way I would if I were trying to write software that I was trying to deliver to someone. Another example might be a scientist programming a one-shot experiment. So, okay, so there's supposed to be this little animation thingy, but it didn't really animate. Anyway, so what you can see up there at the top is that we're trying to slice across people and just go with intent to sort of de-silo. So how can we do this? How can we use intent as a basis for de-siloing? So what the challenge is to make future end-user software engineering tools about the intent and not about the person. So let's see how that goes. Let's consider a medical scientist, might have some background in programming, and that medical scientist has a lab application to collect sensor data. So let's think about her intent. Let's say it's broken. And so her intent is probably something like, fix my broken lab application or add capabilities to last year's lab application, but it's not find a wonderful new tool that will give me ways to guard the quality of my application. Probably that is not the intent that she has. So if we really focus on what is her intent like, what can we do with that? Well, here is where some theories can really help us. So intent resides in people's heads. Therefore, it makes sense for us to look at some applicable theory of how people think. And one such applicable theory is the model of attention investment. So a common software engineering assumption sometimes is if we build a wonderful new tool, of course people will use it. And what this model of attention investment tells us is that's not really consistent with people's intents. So what attention investment asks us is, why should they? It consists of three pieces: perceived cost, benefit, and risks. And so the emphasis here is on perception. So here we have this lab scientist. She has a broken lab application. She wants to fix it. And so she's thinking about how much time it's going to cost her to use some wonderful new tool, what the benefit she thinks will be from that wonderful new tool. which may not be clear without paying the costs, and the probability that she'll go down that path and still not get the benefits. So let's look at that a little bit more closely. Here's this lab example. Suppose the scientist has tried to fix her lab application using her ordinary editor. It's not working out very well, and so she thinks, I really need something better than just editing. So she kind of looks around and she spots a tool that might help. And she ventures to touch it once. So her first impression is when she's going to get a perception of the cost to learn and use that tool. And one of the things we've discovered in our lab studies is that that first impression is everything, which is really kind of a bummer because that's often when your tool is at its worst because it doesn't have very much stuff yet to build on. Anyway, that's determining her perception of cost. She's also thinking of risk, and she's weighing her perception of costs and risks from that first impression against what she thinks the benefit will be. And if the costs and risks outweigh the benefit, then she doesn't use the tool. So then that is kind of prescriptive for us because what it tells us is that future end-user software engineering tools should then target a very intent-based who by, number one, connecting to the end-user developer's intent whenever it arises, and number two, somehow enticing the user to take appropriate software engineering steps by making explicit at that moment the likely costs, benefits, and risks. So this then leads us to, well, how would we go about that? And there are several possible strategies that people have already begun to use. One of them is here on the screen. So the first one I want to talk about is, let's call the research and then serve existing intent. So an example of that is the Y-line debugging system pioneered by Andy Coe and Brad Myers. And so there what they did is they studied a bunch of people debugging and learned that why didn't were the most common questions by far that people were asking. So they researched and then they built a system to serve exactly that intent, why. Then the second strategy that intent offers up to us is what we might call infer and then serve intent. So an example of that from end-user software engineering's debugging and design is the Idea Garden, which is a project I've been involved in. So with the Idea Garden, somebody is programming along and having some sort of problem and they get stuck and they don't quite know what to do. So there's a little thing they can bring up that's context sensitive, and that's the Idea Garden. And so first, it gives some idea of what it's inferring about what they're doing. So it's kind of saying, okay, I've noticed you've done this thing, and then it finishes making the inference to make your script work for all rows. So that's what it's inferred they're trying to do, and then the rest of this gives them the guidance that would enable them to do that. So that's an example of the infer, then serve intent. And then a third intent-based strategy, which you sometimes see, is to generate intent. And so a great example of that is the PEX for Fun system, which is based on turning programming into a game. It's by Nikolai Tillman and his colleagues. And so here you can see that it's basically trying to entice end-user programmers into this. And so it's pointing out that this is a game and that it's fun. So these three strategies all have something in common that we can learn from. And these things all kind of stem from the model of attention investment as well. So first, targeting end-user intent as of right now. All three of those strategies have that in common. Second, drawing the end-user developer into doing just a little when it can benefit them directly by making clear the potential cost, benefits, and risks. And third, giving the end-user developer supports just in time in their own environment in a way so that they can actually succeed at some little incremental thing that they do. These strategies really work. There are empirical studies on all three of the tools that I've just mentioned to illustrate these strategies and seem to point the way forward toward a more intent-oriented future in our who category. That's another animation that didn't work. Okay, so let's move into the when challenges. How can we de-silo the when? So today's end-user software engineering has succeeded in getting us out of the coding cycle. So it's taken us beyond coding, and that's been awesome. It's added support for lifecycle stages to end-user programming, such as in testing and design, assertions, reverse engineering, refactoring, lots and lots of work on error prevention and detection and so on and so forth. Let me give you just a quick example of the last category. Here's Chris Caffidi's work on TOPEs. This was about enabling ordinary end users to prevent errors, inspired in part by that Hurricane Katrina example that I gave you earlier. And so what they can do is they can name a sort of, shall we say, a type of thing, and then they basically put in various rules about what makes a valid type, and they hook that into whatever environment they have, a spreadsheet environment or a programming by demonstration environment or whatever, and it does error checking. So that's a great example of the kinds of things that we're on today. But for tomorrow, it would be great to get past this notion of just beyond coding. So there are two steps that we need to be able to get outside of that box. Step one, and some of this is already emerging, is that everything that we provide for end-user developers needs to be interactive, so they can do just a little, and incremental, so that just a little works really well, and not trapping them in some kind of mode, because end-user developers usually won't tolerate that. Doing that kind of work already can be quite interesting for us as tool builders and researchers, because oftentimes getting out of this sort of batch-like thinking requires novel reasoning algorithms, and there are lots of examples of people who've done quite interesting things in that arena. So that's step one. And then step two, what we need to do is somehow take those ideas and transcend the one lifecycle phase at a time research silos in favor of bigger or cross-cutting visions. And one way that I can see to do that is to frame end-user software engineering problems in terms of human activity, not just software engineering lifecycle phase. So basically, the challenge is to get beyond coding. All right, another one of those animations that kind of failed. All right then. So let me illustrate this with Frieda's story. Frieda is a real person, although this isn't her name, and this is a real story. And so Frieda is an accountant. And every year, her company issues this year's annual budget tracking update. And so Frieda needs to take care of that in her department spreadsheet. So when this happens, Frieda has 4 variants of this spreadsheet. She has last year's company budget tracking spreadsheet, and she has last year's department budget tracking spreadsheet, and she has this year's company budget tracking spreadsheet, and she has the department budget tracking spreadsheet that she's building right now to solve this problem. So that's what she's got. And then what she does is she proceeds almost like last year in a very iterative way. So she starts by trying to copy many of last year's changes that she made to the department spreadsheet into this year, but some problems come up because the copy-paste often adjusts itself in a way that isn't what she had in mind, but she keeps her eyeballs on it and tries to notice when things go wrong here. Sometimes she notices and sometimes she doesn't, and she fixes them if she notices. But, of course, this is pretty error-prone, and she knows it is. So she saves lots of intermediate versions just in case along the way. So by now, Frieda has a lot of variants of this program. So in this process, just these 6 bullets above, we can see that a lot of lifecycle steps got basically touched. There was reverse engineering, there was reuse, there was implementation, there was testing, there was debugging, and it was all intermingled. So we certainly can't imagine Frieda going into separate tools to try to deal with all of that stuff. This is where the insight comes. So if we really think about, well, how does Frieda see what she's doing, we realize that we might characterize that as something like exploration or some other word like that, which is a more holistic notion than those 5 life cycle phases that I just listed. And it even includes more than those 5 life cycle phases. So it also includes Frieda sort of backing out of partial solutions and puzzling about odd behaviors and mixing the best bits of some previous partial solutions. So those things aren't even in any particular life cycle. So the possibility then is to try to build approaches that sort of make first class the end user developer's intents. Here we're calling it explore, to get approaches that transcend individual life cycle phase silos. There are people already working on this. My colleagues and I are making a very early emerging start, and I think a few other people are too. So this is a possibility that you may see emerging in the near future. Now let's talk about kind of a meta topic, which is de-siloing our knowledge about end-user software engineering. And here it's understanding the why and the how of what make our tools work in end-user software engineering. So here we bring theory to help us. The problem really is that we need to de-silo our knowledge through unifying principles to really help us understand how the gains that we make and the tools and the techniques can all fit together. Our opportunity to do this is to harness theories on how humans reason and problem solve in this kind of setting. So there are lots of reasons to do this. I want to talk about 3 of them. One of them is that this gives us strategic insights. This helps us see the way to go, and it helps us see it even if we are kind of new tool builders rather than very, very old, experienced ones. So Jim Herbsleb argued this quite well at a keynote at EUSE in 2014. Mary Shaw wrote what may be the seminal paper of it back in 1990 in IEEE software. And so in Mary's paper, she pointed out how theory had really helped with strategic insights in certain engineering fields. So one example that she offers is in construction. So people have been building buildings for, hundreds of years, thousands of years. They did this just fine without theory. They cobbled together these houses, and mostly they stood up, and everything was just fine. But they couldn't get past that. They couldn't build skyscrapers, certainly. I mean, yeah, there was the occasional brilliant person who figured out how to do a pyramid, but that was far from widespread. And then theory came along, things like theory of statics and strength of materials, that enabled skyscrapers to be built quite routinely. And we've even seen benefits like this in computer science. And so back in the old days, only really master software developers, very, very experienced ones, could build compilers. But then when formal language theory became well known and kind of integrated into compiler building, it became routine for even ordinary undergrads to build compilers as part of their undergrad instruction, which is the way it is in most undergrad programs in computer science these days. So theory can really change what we can see to do and bring those capabilities even to people who have not yet achieved master craftsman status. Second, they can really help us understand what kind of studies to design and how to interpret our results. Let's see, do I have a separate example of that one? Yes, I do. Let's see here, sorry. Not quite yet. And it can help us connect tools after the fact. All right, so let's gallop ahead here. So first, the strategic insights. Besides the example that I just offered from Mary Shaw, we have attention investment, which we talked about earlier, which was really helpful to a number of tools in making them be accepted and used effectively by ordinary end users. And the great thing about some of these theories is they're almost prescriptive. Once we understand what we don't understand, it tends to give us ideas about how to improve acceptance and adoption. Another example on the empirical studies, well, actually several examples here. First of all, in a recent paper by Emerson Murphy-Hill, he talked about how work design theory helped him not only figure out the design of his study and the things to go after, but also specifically helped him design particular interview questions that he was using as part of that. Another great example is human error theory, an empirical framework that Andy Ko and his colleagues used to do a really deep study in the kinds of errors that programmers make. And then finally, it can help us in interpreting the results we get. So Laura Beckwith and her colleagues used this to really understand why the gender differences that they were getting in feature usage, why they were existing, and how we might interpret those. And then example 3, connecting the dots. So information foraging theory is a theory that's been very good for that. That's a predator-prey theory on how people seek information. It reveals behaviors that in various end-user software engineering settings, and it's also been used to show the commonalities and design patterns across 20 different software engineering tools spanning debugging and factoring and refactoring and reuse, and so basically all across these previous silos. So how can we take all those things together then and go onward? Well, one thing that I think is really important to realize is that even though, well, we know that end-user software engineering owes a lot to both of its parents, HCI and software engineering, but it also has some things to bring back to just classic software engineering. One nice thing about the end-user software engineering is it tends to bring a magnifying glass, a lens, to the problems that anybody might be experiencing in software engineering, not just end users. It makes these visible in a way that makes it possible to bring some of the gains back to classic software engineering. One example is a new vision of the developer tool partnership, in which the developer's motivations matter more than what the tool sort of wants of them. So again, a first-class focus on intent, and this can benefit not only end-user developers, but professional developers as well. For example, the gender differences that Laura Beckwith found in end-user developers turned out to also be the same kind of gender differences that were being experienced by professional developers. And here we're talking about in tools themselves with implications for how tool features should change. Another example is the Y line for Alice, which I showed earlier. There's a little picture to remind you of that why question. That ultimately led to the Y line for Java to benefit professional programmers. So in conclusion then, why should we de-silo? Well, really, I think that big, transformative, visionary gains require getting outside the box or outside the silos. And to get us there, I've talked about challenges in 3 dimensions. The WHO challenge, focusing a great deal more on the end user developer as an intent. Opening the door to intent-oriented operations, which make us think about manipulating and rewarding intent, inferring intent, targeting intent, sort of a whole new way of thinking about things. The when challenge, beyond lifecycle silos. So here we're thinking about allowing the end user to be opportunistic, incremental, interactive, and not moded into some research silo that is convenient for us but not for them. And then, of course, the why and how challenges, using theory as a foundation, a strategic guide, and a connector. Let's see here. Oh, yes, those are my animations. So I think that going in these directions is not easy. It really requires us to scratch our heads and think deeply, but it's worth it. And I think it can bring to big visions beyond one silo at a time. This is my last presentation slide. There is a slide after this for people who download the presentations that sends you a link to our paper, or you can just search on the title of this webinar and that'll get you there too. So I think we are open with plenty of time for questions. I hope you'll send me a whole lot of them.
Thanks, Margaret. That was really interesting. We have a couple questions that came in while you were speaking. The first one is one of the audience would like to know about environments like Mathematica and MATLAB that tend to be used by scientists, but sometimes without reliable results.
Yes.
But they seem to have had, a focus on trying to have very rich, elaborate libraries to enable scientists to do things themselves.
Yes, so that's a great question. It brings out the fact that even scientists, even with lots of technical background, can still be in end-user development modes. And so the thing that really distinguishes scientists doing stuff in MATLAB from, shall we say, professional developers is when they're in the mode of doing an experiment in which what they really want is the results of the experiment, not the software itself. On the other hand, that same scientist might get into a mode where they're trying to create software to release to other scientists to use, and then they're acting more like professional developers. In both cases, it's the same person, but they're in different roles, and so they have different mindsets and different motivations and interests in using some of these software engineering possibilities. And so even environments like MATLAB, then those can indeed be very technical, but we can still take these same lessons and apply them there. Things like intent, when somebody is trying to just get the answers, and think about how can we help that person without moding them in, and the same messages that have come across for the other environments. So I hope I've answered what you were getting at there. Scientists definitely count.
Thanks. To the audience, I hope you'll type some questions into your question and answer window. We have plenty of time, and there's just a few questions that have come in so far. Along the way, kind of just as an aside, you mentioned differences between male and female programmers, and one of the audience was wondering what you were talking about. So
yes.
Give that a little summary.
Yes. So a lot of us have been doing some investigation into how problem-solving tools like programming environments, debuggers, things like that, how those match with the way people problem solve. And people have lots and lots of individual differences on how they problem solve, but a lot of them tend to align by gender. And so it turns out that since a lot of the software was written originally by males, then many more of the supports in these things tend to align statistically with male styles of problem solving. And so knowing about those things lets us add to the tools additional alternative problem-solving mechanisms that will just get at a broader range of problem-solving styles, and therefore pick up a greater diversity of the problem solvers there, and also really help with the problem solvers that, a pretty big pile of them are not currently served very well, and many of these people happen to be female, although certainly not all of them. If the questioner wants, let me just give one example. So one example is information processing style. So when you're problem solving, you need to gather information. And there are a couple of different styles of doing that. One of them is kind of a depth-first style, very incremental, in which you gather a little information and work with it, do something. Say, for example, try out a bug fix and gather a little more and do something with it, and so on and so forth, and backtrack if things aren't working out. So statistically, males are more likely to use this style than females, and a lot of debugging tools and environments support that style pretty well. The other style is comprehensive, which is more bursty. And so there, the problem solver will want to gather more information before proceeding, and then do a little burst of activities, acting upon that knowledge, and then gather another larger batch of information, and then another burst. So the timing is just different. Neither is better or worse. each of them have advantages and disadvantages, but that style isn't supported as well in today's tools and environments, and that's the style statistically that tends to have more females in it than males. So that's just one example.
I like your example about tinkering. Can you maybe summarize that one too?
Sure, yeah. So tinkering really relates to people's learning styles. So some people, they like to learn about new features and tools by fiddling around with them and sort of playfully doing it, and that statistically tends to align with males more. And females tend to have other ways they'd like to learn about it, maybe to read a little about it in a mini tutorial or something like that. So they're just different learning styles, and again, neither is better or worse. They both have advantages and disadvantages. But a lot of software today is predicated on the idea that the way people will learn how to use new features is that they'll tinker with them. And so that doesn't attract people who don't have that style. And so if they had alternative ways to learn new features that were just really lightweight and easy to get your hands on, then more people would probably be using some of the fancy new features that software producers are putting into their problem-solving environments.
Great. Another question that came in, the person said, I'm sometimes asked about the possibility of programming graphically. Is there any research that this is possibly a fruitful approach? Any success stories?
Very good question. Yeah, there is a whole conference, actually probably more than one conference, but the one I'm thinking of is IEEE's VLHCC about graphical programming. So that conference has been going on for, I guess, probably more than 20 years now. So I encourage you to check the online libraries to find papers in that one. It's called Visual Languages and Human-Centric Computing. In terms of whether there are advantages to programming visually, it turns out that it's not so much about visual versus textual. It's about the affordances that visual programming might enable you to do. And so as Thomas Green, the original inventor of cognitive dimensions, pointed out one time, every notation is better at some things and worse at others. And so as long as you're not strapping yourself into only one notation, let's say only text or only visual, then you have more possibilities to choose the right notation to communicate what the environment needs to communicate at that moment. So for example, dependencies maybe are best communicated with a line, but what is the line between, whether it should be, nodes or text? Well, maybe the text is what it should be a line between. So I think it's not so much a question of visual versus text. It's more of a question of expanding the ways we can express things so that we have more choices to make the right decision for what we're trying to say in our tools.
And I guess we can add that there are a number of commercial graphical programming systems. The most notable I know of is LabVIEW, which is a long-standing commercial success.
Yes. Yes, and I actually consider anything involving direct manipulation to be at least somewhat visual. So certainly the programming by demonstration work, and especially the programming by demonstration work in user interfaces, which of course you pioneered, are great examples of visual programming as well.
Thanks. So the work that you did on spreadsheets was some time ago. And one of the audience asked if there's more work that can be done in spreadsheets, or how are we going to make spreadsheets more reliable, now?
Yeah, great question. So there is an active body of research in the spreadsheet world. I worked in spreadsheets for something like 10 years. Let's see, was it 10? Maybe it was more than that. But I certainly wasn't the only one. Still active in that world. Feline Hermans is doing quite a lot of work in spreadsheets. I think Chris Scafidi has some fairly recent work in that domain. There are several other people. I think the best places to look for that kind of research, which continues to improve the spreadsheet world, would be VLHCC, the IEEE conference that I mentioned before on visual languages and human-centric computing. So that's one place that you see that kind of research quite often. CHI, the Human-Computer Interaction Conference, seems to have some spreadsheet papers about every year. And in fact, EUSE often has spreadsheet papers as well. I remember one from EUSE 14. I haven't looked at EUSE 15 yet. Actually, I think there was more than one in EUSE 14. I remember one from EUSE 13 too. So yeah, all three of those places have continuing progress in spreadsheets in terms of, well, all kinds of things. Ability to generalize spreadsheets, error prevention, error detection, all different, sort of expanding on the capabilities, all different kinds of work in that area.
Thanks. Another question goes to the level of experience for end-user programmers, and suppose someone only has a single course in programming or even no courses in programming. Are they able to succeed and use some of these techniques?
Yes, okay, another great question. So there are many end-user programming approaches that are very intended for people with no programming background. So I think one of the great examples is the CoScriptor slide that I showed early in the presentation. There, what somebody does is they bring up an ordinary web page and they automate the operations that they'd like to do on it. So for example, let's say they bring up their favorite flight search page and they automate the things that they like to put in there. So maybe they always check off that their favorite airline is, I don't know, United, and that, you know, they prefer morning flights, and so they, you know, they always do this stuff when they search for flights. The thing that changes is maybe the date and certainly the location. So they can put those things in while the recording button is on, and CoScriptor is recording all of those actions and turning them into something that they can rerun, and it's showing them all of these actions in a textual form so that they can edit it. So for example, they might take out the date and the location lines because they're going to want to put those in each time, and they can replace those with pauses that let them fill in the right boxes. And then everything else can stay the same, and now they've got a script that will run a lot faster than having to mess around with all the checkboxes and so on and so forth, that they do the same each time. So there, no programming background was required at all, and yet what they have is a program.
Another question goes to the programming style, and somebody wants to know if functional programming is easier for novices or end-user programmers compared to procedural programming or object-oriented programming.
Yeah, that's a good question. I don't think that anybody has ever really found a paradigm difference. There's been lots and lots of, I don't know, religious wars, people giving opinions about one paradigm or the other being superior, but I really think that the notation of that language and the environment it's in really turn out to be much more important than the paradigm. So for example, LabVIEW, the example language that we looked at with the virtual instruments that you wire up, there it kind of makes sense to be using what amounts to a data flow or a functional paradigm, because what they're really trying to do is take those wires that are connected to their sensors and kind of push them through some library routines to get an output. So it seems like to match that domain to what people are used to doing anyway, which is wiring things up into other things, then maybe the shall we say the closeness of mapping, the closeness to the way people are starting out thinking things, is really telling us that in that case functional is the best. But on the other hand, this programming by demonstration example I've been talking about with CoScriptor, there it seems very procedural. I mean, you're thinking about it as first click this, then click this, then click this. Well, so that's a procedure, and that's the way you think about it, and in fact that's even what you're demonstrating, so it seems to make sense not to switch into some other paradigm about that. And people have argued that object-oriented is more natural as well, and here again I think it really depends on what people are thinking, you know, what your users are actually starting with as their model of what they're trying to work with and do, and then come up with a notation that works that way.
Okay, I think we have time for maybe one last question, and somebody was interested in Frieda's story. It seems like you had a bunch of issues, but there wasn't really a resolution or a technique that helps her?
Yeah, okay. That's true. And that's because this talk is actually about the future of end-user software engineering. So what I was really trying to use Frieda's story about was to show the problem and to show how a life cycle approach just kind of leaves Frieda unhelped. And then it isn't a problem that's well solved yet, but I pointed out that there are people that are trying to think more in terms of Frieda's activity, and of course you and I are in one collaboration that's trying to move in that direction. But that work is early, just starting to emerge. So it's definitely in the future and ripe with opportunity for other people to jump in and do that kind of work as well. So definitely an open problem. Frieda will thank you if you can figure out a good solution to it.
And one question just came in at the last minute. It says, you mentioned differences between men and women in approaching problem solving. Aside from gender differences, have you found any pattern in the stages of problem solving that users move through?
Let's see. I wonder, let's see, aside from gender differences. Okay, I see what you're saying. Yes, there are a lot of different ways to slice individual differences, and gender differences is only one way. Another way, which I think the questioner has in mind, is that your problem-solving style tends to change when you're in a different phase of understanding or working with the problem. And I would agree with that. That makes sense, although I don't know the literature well enough to be able to cite anything. Another way to slice it is by age, because there too problem-solving styles change as people age. And so, and another way to slice it is maybe by cultural background or education background. So there are a lot of different ways to slice individual differences. The really important thing is to be able to support a diversity of these differences so that more and more people can bring their intellects to the table, even if they don't have exactly the same styles as the people who originally were envisioning how to solve a problem.
Great. Thank you for the great talk and the interesting questions. I'm afraid now we've run out of time today. I'd like to thank Dr. Burnett again for her informative presentation and insightful answers to many questions. A special thanks to each of you in the audience for taking the time to attend and participate today. This webinar was recorded and will be available online in a few days at www.sigsoft.org/webinars.html. You can find announcements on upcoming SIGSOFT webinars and other ACM activities at learning.acm.org and www.sigsoft.org. The next webinar will be on June 25th with a presentation by Satish Chandra, Senior Principal Engineer at Samsung Electronics, titled, Are You Getting Traction? Tales from the Tech Transfer Trenches. That said, this is Brad Meyer saying goodbye for now. Thanks again for joining us. Hope you will join us again on future webinars. Goodbye.